Balancing redox equations. When you have a redox reaction that occurs in aqueous solution, the equation can be very difficult or almost impossible to balance by inspection, the way that we've learned to balance them up until this point, where you just kind of look at it. And so what we do is we use a half reaction method. So we take the overall reaction and we break it into two half reactions. We find the thing that's being oxidized, and we write a half reaction for that. And we find the thing that's being reduced, and we find a half reaction for that. We balance each of those separately, and then we add them back together. I can tell you're really excited about this. Okay, so here's a redox equation, a reaction. Aluminum plus silver ion forms aluminum ion plus silver. And you may look at that and say, well, what's wrong with that? Isn't it balanced already? There's one aluminum on each side, and there's one silver on each side. But for a reaction equation to be balanced, it has to have the same charge on each side. And here we have a +1 charge on that side, and this side has a +3 charge. It's not balanced. So first we're going to assign oxidation states so that we can see what's being oxidized and reduced, and then we're going to divide it into two half reactions. So what's the oxidation number for aluminum? All by itself? 0. And for silver ion? +1. If you have a monatomic ion, there's just one element, the charge and the oxidation state are the same number. How about over here? Aluminum 3+, +3. And silver, the element, 0. What's being oxidized? Aluminum. The aluminum is going up in oxidation number. The aluminum is losing electrons. Oxidation is loss of electrons. So for the oxidation, I'm just going to write the part that has aluminum. So I'm going to take aluminum goes to Al3+. And then the reduction, silver ion is being reduced to silver. It went from +1 to 0. So I'm going to put that down here. Ag+ goes to Ag. Everybody okay with that? Now we're going to balance each of these half reactions. First we're going to look at mass, numbers of atoms of each element, and then we're going to look at charges. So Al to Al3+, we already have one aluminum on each side, so the mass is balanced, but the charge is not. This side is +3, and this side is 0. We balance the charge by adding electrons where needed. So we need 3 electrons, and we're going to add them on this side so that we can have the charge be 0 on both sides. +3 electrons. So now I have 3 positives and 3 negatives. That's 0, and I have 0 on the left side. They don't have to add up to 0, but they have to be the same on each side of the arrow. Down here, I've got Ag+ and I've got Ag. So I need an electron on this side to get rid of that charge. So I'm going to stick it in here. I left room for it. So those are balanced half reactions. When the overall reaction occurs, though, the aluminum is losing 3 electrons. Those 3 electrons have to go to someone. The silver ion is only taking 1 of them. The number of electrons lost and the number of electrons gained has to be the same. So we have to get this to be the same, 3 and 1. So what we're going to do is we're going to take this equation at the bottom and multiply the whole thing by 3. Say, well, actually, there's 3 of those happening. 3 silver ions, each taking 1 electron, would get rid of the 3 electrons. Yeah. So here I've multiplied that out. 3 silver ions plus 3 electrons gives us 3 silver atoms. Now if I take these 2 equations and add them back together, here's 3 electrons being given and 3 electrons being used. Those cancel out just like the spectator ions do. So those don't end up showing up in the final equation. So I get aluminum plus 3 silver ions makes aluminum 3 ion plus 3 silver atoms. Then you should always double check. We've got 1 aluminum, 3 silvers, 3 silvers. Total charge on the right side is plus 3. Total charge on the left side is plus 3. This one you could have balanced by inspection, but some of them you can't. Any questions? I think we've got another example coming up here. Oh, list of, oh yeah, there's that. Okay, so here's the rules. First step is assign oxidation states, separate the overall reaction into the 2 half reactions, and then balance with respect to mass. That last one was easy, but sometimes there's hydrogen and oxygens running around. So first balance everything but the hydrogen and oxygen. Then if you need oxygens on one side or the other, add water. And now if your hydrogens are messed up, add H+ as appropriate. And then if it's a basic solution, you're going to add an equal number of hydroxide ions to both sides. We'll get to that later. Balance them with respect to charge by adding electrons. Make the number of electrons in both half reactions equal. Add them together and check. Easy peasy, right? I'm sorry I have to do this to you. Okay, let's balance this one. First step, oxidation states. What's the oxidation state of H+? +1 is the charge. How about chromium? 0. H2? 0. There's 2 hydrogens bonded together. Overall, the charge is 0. They have to add up to 0. They must both be 0, because they have to be the same. And then here, +3. So the hydrogen is going from +1 to 0. It's being reduced. The chromium is being oxidized. When you're just balancing this, you don't actually have to identify which is which. You just separate them. So we're going to have H+ going to H2, and we're going to have Cr going to Cr3+. Why did I put an O in there? Because I'm so used to writing H2O. There's no O there. It's just H2. Brain fart. Well, let's balance this one with respect to mass. I have 1 hydrogen atom here, and I have 2 there. So if I put a 2 in front of the H+, I have 2 hydrogens on each side. Let's balance Cr to Cr3+ with respect to mass. Done. It was already balanced. Now charges. Total of +2 charge over here, 0 over there. I'm going to need to throw in 2 electrons on this left side. So 2 negatives plus 2 positives, total charge on the left, 0. Total charge on the right, 0. Chromium to chromium 3+. So if I put 3 electrons over here, then this side will have a 0 charge. So I did mass, and then I did charge. Now I have to get 2 and 3 to be the same number. Least common multiple. What's the least common multiple of 2 and 3? 6. So I'm going to multiply this top one by 3, and I'm going to multiply the bottom one by 2. I'm going to distribute those, okay? Okay, so this then becomes 6 and 6 and 3. And down here this becomes 2 and 2 and 6. And when I add these together, the 6 electrons on each side go away, and I'm going to copy down what's left. I've got 6 H plus. I'm going to be good and put my state symbols back. And I've got 2 chromiums, and that's going to make 3 hydrogen molecules and 2 chromium ions. Any questions?